So this brings us to tutorial 3, where we'll talk about multiple linear regression. Multiple linear regression is a model that is still very commonly used in lots of scenarios, and arguably is one of those models that we can really use to be sure on what our modeling does. It leads to a lot of mathematical insights. So for just about anything, we will have multiple pieces of information. If we want to make predictions, it will generally help us to have more kinds of data. Using more data will generally make us better at predicting. Now, of course, that means that's only true if multiple pieces of information kind of don't share all the data. But usually different pieces of information provide distinct information. For example, if I might want to estimate, say, how someone will be at class. We mentioned that earlier. You can say, what are predictors? Maybe past grades, maybe age is a predictor. All kinds of factors can be predictive, and many of them will be weakly predicted. So I want to also already have a remark here, and we will talk a lot more, which is making predictions is relatively easy. That's why it's so useful. That's why much of, say, data science and industry is driven by making prediction. But interpreting predictions is relatively impossible. It's extremely difficult, both from a statistical power perspective as well as from a causal inference perspective, as we already discussed earlier in the course. So, we've seen earlier today linear models. In that case, the output is a linear weight multiplied by some input. Alternatively, we can also add an intercept there, where we can say the output here is some linear weight times an input plus a bias, an intercept. Now, that is a simple linear model. The input is a scalar, the output is also a scalar. Now, we could also have a scenario where the input is not just a scalar, but where it's a vector, where you could say it's multiple features. In that case, we can also have a linear model where we can say y is basically theta 0, that's just the intercept, plus theta 1 times x1, plus theta 2 times x2, plus and so on and so forth, up to theta d times xd. Now, more generally, in vector form, for one data point at I, we could say yi, the output, is theta transpose, so this is a vector, times xi. And now this, of course, would be the case for the first data point, the second data point, and so on and so forth. And now in this case, we have theta, which is a vector, which is transposed, and xi, which is another vector, which contains 1 first, and then xi1, xi2, and so on and so forth. So I want to remind you what's happening here. So here we have a baseline, theta 0. Now a trick that we often do in machine learning is we put into everything that we use to make predictions, we put a 1, either in the beginning or in the end. That 1 then allows kind of the weight that we have from here, the theta 0, to be the bias. And that way we don't need to keep this syntax where we can always say it's x1 times theta 1 and so forth plus x0. And then we can use this vector syntax here. Now we can build this up to a matrix one where we can say y, if we now want to predict a vector based on a vector, we can say y is going to be x, a matrix, times, x, an input vector, times theta, which will be a matrix then. No, so then we have y is y0, y1, y2, and so forth. That's the vector that we predict. Here we have the x multiplied with all the thetas. Now, if we think about mean squared error, we can have a geometric interpretation about that. The mean squared error computes the average error between the model predictions y hat and the true y. Now we're back in the one-dimensional version of that, where we can say the mean squared error is, and then we have the model prediction minus the true outputs. So model prediction is what we have here in red. Now this is our model. Now the model prediction is yi hat, which always lies on this red line here. yi is where the data is. Now, in the geometrical interpretation, the error that we have here is the difference of the yi from the yi hat given an xi. So therefore, we can view this, the model, the mean squared error is basically just the squared distance of these points from the red line. Now, what if we go into higher dimensions? Now, like here, it's always parallel to the x-axis. Can we have a similar geometrical interpretation if we go to higher dimensions? And yes, we can. So the geometric interpretations, what we have is y here, the prediction of y is theta 1 times x1, where x1 is now a vector, plus theta 2 times x2, and so on and so forth. So we have x1, so one vector going in. We have another vector going in, x2. Now they will both be weighted by the thetas. So we have our estimate y hat is going to be theta 1 times x1 plus theta 2 times x2. So we take these two and we weigh them by the relevant thetas that will scale each of them. Now, this is theta 1 x1, this is theta 2 x2. Now the sum of the two of them is the model prediction. So what we do is we take these vectors and we just add them up together, giving us y hat. And now y is a point in that space. Now, what is the error that we are making? Well, it's still the difference between y and y hat. It's just now y minus the sum of these, theta 1 x1 plus theta 2 x2. And that's the error. And now that error is the distance between these 2 points geometrically. Now that error, we can move it back to the origin, in which case this is our error. So if we do regressions in like a vector space, then the errors will also have the form of vectors. And now what's the mean squared error? Well, it's theta 1 x1 plus theta 2 x2 minus y squared. Now this is if it's scalar. If it's not scalar, we will have that error transposed times the error. Now we can say, well, what's the best estimate that we can have of that? The one that minimizes the mean squared error. Well, theta star here, our best estimate, is the one theta that minimizes this whole thing. So this thing that minimizes the error. That's the definition. The best theta is the one that minimizes our average our errors here. So here we then have x times theta minus y, and then we have the 2 norm of that. That is the error here. And now this is just the sum over all I of yi minus theta transposed xi. Now that's the prediction of the corresponding dimension of y. Now we can, as before, we can for each dimension differentiate this thing here, set it to 0. So here we have 2x transpose x theta minus y, just applying chain rule to this. And now that means that the best estimate that we get from mean squared error is here we have x transpose x inverted times x transpose times y. This is the equation for mean squared error regression. That's the equation for linear regression. So what do we have here? Here we have a correlation matrix, x transpose x, that we're going to invert times x transpose times y. And then, of course, we have noise as before. Noise will be different. It will depend on the index. So here we have the full form theta star is argmax over theta of the log likelihood. Keep in mind the log likelihood for the mean squared error will take this form. Now here we have this first part of the Gaussian, the log of that. Here we have this squared thing. This is just the vector version of the squared error, where we have y minus x theta transpose y minus x theta, where n is the number of data points and d is the number of features or stimuli. Okay, so we differentiate and set to 0. Here we have the maximum likelihood estimate. Same as mean squared error when the noise is Gaussian. So in the notebook, you will build a design matrix for input x and calculate mean squared error, maximum likelihood estimation solutions for matrix forms. Have fun.